Okay, so here we have a capacitor problem, and anytime there's a problem with numbers, you just have to keep an eye on me because I'm just terrible with adding and subtracting and multiplying and dividing, even using a calculator. So if you think I made a mistake, probably did. I'll probably fix it later, and if I don't, email me. We'll see. Okay, so we have a 0.2 millifarad capacitor. It was 20 volts, so it was already charged, until a switch in the circuit was opened at time t equals 0, causing the voltage to vary with time as, and then we have this function that's telling us how our voltage in our capacitor varied. And the first question said, did the switch action result in an instantaneous change in V of t? Well, we hope not, because capacitors cannot change voltage instantaneously. So that's against the rules. They can't. So, but let's double check and make sure. So we said it was 20 volts at 0 minus. So 0 minus means before 0. So all the way up to 0. And then at 0 plus, so right at 0, it starts acting according to this function. So V of 0 equals, so I'm just plugging into V of t here, equals 60 minus 40 e to minus 5 times 0 equals 60 minus 40 e to the 0. Anything to the 0 is 1, so this is 60 minus 40, which is 20 volts. So good. No, it did not change. So no. Excellent. Okay. Did the switch action result in an instantaneous change in the current I of t? Well, that's possible. So in a capacitor, current can change instantaneously. This is key. So this is real important. I'm just going to write this. So capacitor voltage cannot change instantaneously, but note, current can. And then inductor current cannot change instantaneously, but voltage can. Okay, and these concepts, you got to get those. So that's real important. Okay, so did the switch action result in an instantaneous change in the current? Well, it might have. It might not have. Well, we just have to find out. So what we know is that I at t equals 0 minus was 0 amps. Okay, so how do we know that? So it was charged, but the switch was open. So we had some sort of circuit. We don't know what it was. So we had stuff, okay? But we had a switch, and it had a capacitor. So don't know what this was. Don't know what the circuit was. But the switch was open. The capacitor was charged to 20 volts. But if the switch was open, then there was no current flowing, and under DC conditions, a capacitor acts like an open circuit. So it was doing that. So it was just, there was no current flowing. So that's what happened at t equals 0. Now, we also know that the current for a capacitor is I equals C dV dt. Okay, so once we get to t equals 0, well, now all of a sudden we have a function for the voltage. And so now our current is going to equal the capacitance times the derivative, the time derivative of the voltage. So the capacitance was 0.2 millifarads, so 0.2 times 10 to the negative 3. And the voltage was 60 minus 40 e to the negative 5t. So that's 0.2 times 10 to the negative 3. And then the derivative of this, the derivative of 60 is 0. The derivative of negative 40 e to the negative 5t is negative 40 e to the negative 5t times negative 5 from the chain rule. And then if we plug in 0, so I of 0 equals 0.2 times 10 to the negative 3 times negative 40 times e to the 0, which is 1, times negative 5. And if you do that out, I believe you get 0.04 amps. If you multiply this out and you don't get 0.04 amps, then I probably did something wrong. So, did the current change instantaneously? Yes. Current did change instantaneously. Instantaneously. It changed instantaneously. Okay, so that was part B. So how much initial energy was stored in the capacitor at t equals 0? So that's part C. How much energy did it have? And energy, doesn't your book use W for energy? I think it does. Okay, equals 1/2 CV squared. So at t equals 0, then this is what it had. And remember, it doesn't matter if we talk about 0 plus or 0 minus, because the voltage doesn't change instantaneously. So at 0, the voltage is 20. So we're not talking about on one side of 0 or on another side of the 0. So the energy, I'm just going to write energy so that I don't worry about the symbol, is 0.5 times the capacitance is 0.2 times 10 to the negative 3 times the voltage was 20 volts squared. And when you do all that out, I believe you get 0.04 joules. So you should check that and see if that is in fact what you get. Okay, in part D, how much final energy will be stored in the capacitor at t equals infinity? So energy at t equals infinity. Okay, so we want to know, well, what is the voltage at t equals infinity? Because the energy depends on the voltage. That's the only thing that's changing. So the energy is 1/2 CV squared. C's not changing, the voltage is changing. So we need to find V at infinity. So let's look at our function for V. V is 60 minus 40 e to the minus 5t. Well, let's take the limit of this as t goes to infinity. And note that when you have a negative exponent, so e to the negative infinity, that's 0. So if you don't remember from calculus, let's just look at this. So if I had e to the negative infinity, that's the same as 1 over e to the infinity. And let's just think about what that means. Let's think about 1 over a really, really, really big number. Okay, that's really close to 0. So as we get closer and closer to infinity, this is getting closer and closer to 0. Okay, so this is going to 0. So the whole thing equals 60. So the volt, 60 volts. So at infinity, or after a long time, which is how they say it in the problems, after a long time, the voltage in the capacitor is 60 volts. And so the energy equals 1/2 CV squared is 1/2 0.2 times 10 to the negative 3 times 60 squared, which according to my notes is 0.36 joules.